So our next topic is Norton's theorem. Norton's theorem states that any linear and bilateral circuit can be simplified to a circuit, a current source parallel with a resistance Rn and RL. Okay, so that means any kind of linear and bilateral circuit, we can convert that circuit to a current source. That one we call it a Norton current, IN, okay, or ISC, okay, parallel with a Norton resistance or equivalent resistance, just same as the Thevnin resistance, and a load resistance, okay. I already explained you my video of Thevenin's theorem, what is the linear and what is bilateral, okay. So now just go to the problem and I will show you how to solve a problem by using a Norton's theorem. Just like Thevenin's theorem, there is two type of problem in Norton's theorem also. One is the black box problem, this one, and another one is the just a normal circuit, and they just told you to calculate some load current. Okay, so I will show you both of the case. First is the black box problem, is the type 1. So here the question is same as the Thevenin's theorem. They told you the RL is 5 ohm, load current is 2 ampere, RL is 15 ohm, load current is 1 ampere. If the RL is 35 ohm, what about the load current, right? In Thevenin's theorem, we got the answer is 0.5 ampere. Now let's apply Norton's theorem and let's see what is the result. As per the Norton's theorem, we can replace this circuit by a current source IN, a resistance Rn, and the load resistance. All three is in parallel, right? Here we have the load current IL, okay? By the current division rule, we can write down IL load current will be Rn, the opposite resistance, divided by total resistance Rn plus RL into IN, okay? Here they provided if the value of RL is 5 ohm, then load current will be 2 ampere. Then we can write down 2 ampere equal to Rn divided by Rn plus 5 into In. Okay, this will be the equation 1. And another equation will be 1 equal to Rn divided by Rn plus 15 into In. Okay, if we just solve these two, then we will get Rn into In equal to Rn plus 15. From here we can write down In equal to Rn plus 15 divided by Rn. From here also we can write down In equal to 2Rn plus 10 divided by Rn. So we can just equal these two. Then we can write down Rn plus 15 equal to 2Rn plus 10. From here we can write down Rn will be 5. Now if we put the value of Rn in this equation 3, then we will get In will be 2 into 5 plus 10 divided by 5. Then it will be 20 by 5 is 4 amp. Okay. So just move this circuit. We can write down 4 ampere current source and parallel with 5 ohm Rn and 35 ohm load resistance, right? Now they told us to calculate the IL. We can write down IL will be 5 by 40 into 4. From here we can get 0.5 ampere. So you can see the current we got from the Thevenin's theorem and the Norton's theorem is exactly same. So just the way of calculating the current is different. This is the problem of the black box, and I think you already understand for the black box problem how to apply a Thevenin's theorem and how to apply a Norton's theorem. Just the equivalent circuit is different. And I think you already understand Rn and Rth is exactly same and is equal to R equivalent. Okay. Now let's go to the type 2 problem and let's see how to apply the Norton theorem in the type 2 problem. So we will use the same circuit as Thevenin's theorem, and we will apply the Norton's theorem and try to calculate the load current. So let us draw the circuit. This is the circuit diagram, and here they provided this is the load terminal A and B. This is the load resistance. Just like Thevenin's theorem, I told you the steps, right? Here also I told you the steps. First, draw the equivalent circuit. Step 1. So, what we can draw? A current source, ISC, short circuit current, or we can write down IN, okay? Parallel with a resistance, we can write down R equivalent or RN, not on resistance, and parallel with the load resistance, RL, okay? So our goal is to find out the value of ISC and find the value of Rn or R equivalent. Okay. First, for this step, we can write down this is step 2 and this is step 3. For step 2, the first step will be just same as the Thevenin's theorem. What do you need to do? Remove the load and short the load terminal. In Thevenin's theorem, what you did, just remove the load terminal and it is open circuit. But so for the Norton theorem, we need to remove the load resistance and short the terminal. Why? We need to calculate the current, not the voltage. For the open circuit, we can calculate the voltage. For the open terminal, there is no current. So how we calculate the current? We need to short that particular terminal. Okay. Then calculate ISC in that short terminal. Okay. So let's go to the next page. This is our circuit. Fifteen, 5, 5, 5, and this one is the RL, right? So what do we need to do? We need to remove this resistance equivalent to step 1, step 2A. Remove this one. So let's remove the load resistance and short the load terminal. This is the step 1. Okay, here is 5, here is 5, and this is the, we need to know this ISC. Okay, now we can apply KCL, but as this is the very simple circuit diagram, we can easily write down ISC will be 15 divided by 5 equal to 3 ampere. It's very easy, but as you just learning the network theorems, so maybe this is not that much easy for you. So I will prefer just apply KCL. Okay, so this point we think the voltage is, we assume the voltage is V. Okay, here the voltage is 15. Here the voltage is how much? Voltage is 0 volt. Okay, and as this point is 0 volt and this point, the A terminal and B terminal is the short, there is nothing in between the A and B. That means the voltage at B terminal is same as the voltage at A terminal. That means we can write down this V equal to 0 volt. Okay, now just apply the KCL at point A. Then we will get 0 by 15 divided by 5 plus 0 minus 0 divided by 5 plus ISC. Right? Here we assume, we know this is 0 volt, but we assume that this particular voltage is max or higher than the other voltage. Why? Such that the all of the current will be outgoing. Then all of the current sign will be the same. Right? From here we can easily get ISC is equal to 3 ampere. From here you can see the current will start flow from this side. Okay, And here you can see when the current is appear here, in that time they have two choice, flow through the 5 ohm and flow through the 0 ohm, right? So what current will do? Just flow to the low resistance path and get back to the voltage source. So no current will flow from this 5 ohm resistance. This will be 0 ampere. That's why we get 3 ampere. This is 3 ampere and this all 3 ampere will be go from this load terminal, short load terminal. Okay, so from this circuit we find out the ISC will be 3 ampere. Okay, now go to the step 3. That means we need to now calculate the equivalent resistance Req or Rn. Okay, Req or Rn is exactly same with the Thevnin resistance. Okay, from that one, first redraw the circuit. 15, 5, 5 and 5. Okay, so what is the step 1? This is step 3a. What do we need to do? Open load resistance. Okay, step 2, remove the all of the source, or we can write down replace the source with its internal resistance. Okay, and C, calculate resistance from open load terminal. Okay, so what we can do? Replace the voltage source with this internal resistance. The internal resistance of voltage source is how much? Is 0. So the circuit will be looks like this one, right? This is A, this is B, 5 ohm, 5 ohm. Then we can write down RAB equal to 5 parallel 5 equal to 2.5 ohm. Okay. So now we already have the value of short circuit current or IN, and we already have the value of RAB or Rn. Okay. Now just replace this one. Then we can write down this is 2.5 and this is what? 3 ampere, right? And what with the value of load resistance is 5 ohm. So we can write down IL will be 2.5 divided by 7.5 multiplied by 3 ampere. Then we will get how much is the 1 ampere. So if you recall, the answer from the Thevenin's theorem is exactly the same. That means in this particular circuit, now we already applied KCL, KVL, Thevenin and Norton. Every time we got the result of this current is the 1 ampere, right? Now let's go to the simulation and I will show you the how to calculate the ISC, IN and the R equivalent resistance. Okay. And I will simulate this circuit and I will show you the load current here and the load current here will be the exactly the same. From that one we can prove the Norton's theorem. So here you can see the circuit is the same just like the Thevnin. Okay, and we already know the load current will be 1 ampere, right? Now what we need to do, we need to calculate the value of ISC and the value of RTH, and we need to check our calculative result is same as the simulation or not. Okay, now let's go to the next circuit is the calculation of IN or ISC. So what we did, I just replace the load resistance and replace with the short circuit, right? And I connect a ammeter, and you all know the internal resistance of ammeter is 0. That means equivalently this is a short circuit. Okay, so the ammeter reading will be the IN or short circuit current ISC. Okay, so let's simulate this circuit. Here you can see the ISC is how much is 3 ampere and is exactly same with our calculation result, right? So next go to the RTH. RTH and RN is exactly the same, right? So I use the same circuit and I replace the load resistance by the ohm meter. That means I replace the load resistance, I remove the load resistance and I connect a ohm meter to calculate the value of TH or RN or R equivalent, okay? And I replace the voltage source by its internal resistance 0 ohm. Now, as you all know, this resistance meter is reading the value of RN, and this is exactly is equal to the 2.5 ohm. Now, just replace all of this thing by the equivalent circuit. This is the equivalent circuit of a Norton's theorem. Norton's theorem states that any linear bilateral circuit can be replaced or can be simplified by a current source with a parallel of the Norton resistance or equivalent resistance Rn and parallel with the load resistance. Here you can see this is the Rn, this is RL, and this is the ISC. Okay, we got the value of ISC is how much is the 3 ampere. So now change it to the 3 ampere. Okay, so here you can see the value of Rn is 2.5 ohm, the value of ISC is 3 ampere, and the value of load resistance is 5 ohm. Now we need to calculate the value of IL. Okay, so as per the calculation, we got the value is 1 ampere, right? So let's simulate this circuit. Here you can see we got the value of load current is exactly the 1 ampere, right? And that is exactly same with our normal circuit without simplification circuit is also is 1 ampere, right? So now, as I state in Thevenin's theorem, in the same circuit, when we apply KCL, KVL, Thevnin and Norton, in all of the cases, we got the load current is 1 ampere, okay? Hence, Norton's theorem is also proved, okay? Thanks for your time. Please do share this concept with your friends. And if you like this video, please press the like button. It is really means a lot for me. Bye bye.